Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is tutorial 8 and it's also lecture 38. We'll continue from our previous tutorial where we shall be solving some problems related to astrochemistry. Okay, so the first question for today's tutorial is going to be, now we discussed about the idea of wave-particle duality in lecture, correct? Now, I kind of gave you the description that wave-particle duality is applicable to quantum mechanical entities, right? So the statement I'm writing down, wave particle duality is applicable to quantum mechanical entities, and I roughly define these entities as those whose dimensions are of the order of less than or equal to 10 to the power minus 8 meters. Right? This is how I roughly defined the systems wherein wave particle duality is applicable. The question is, is this idea of wave particle duality, I'll just call it WPD, okay, wave particle duality. Well, I mean, instead of writing down wave particle duality with my handwriting again and again, I'll simply put it WPD. There's this idea of wave particle duality applicable to all the molecules detected in space. Right? You understand the question? I discussed the idea of wave particle duality and that it's very important, right? And that's how we even obtained the time independent and time dependent Schrodinger equations, correct? Now, is this idea going to be applicable for all particles detected in space? Are we good, right? I just said that, okay, molecules' dimension is this, etc. I was giving only a qualitative description. But do I know for a fact that wave particle duality is indeed relevant to astrochemistry? What is the answer? The answer is, of course, yes. Okay, right? The answer is yes. And what is the basis? Right? The basis is that molecules as large, okay, right? What is one of the largest molecules detected in space? When we were discussing the idea of molecules detected in space, a few lectures earlier, we're talking about roughly around lectures 20, 22, 24, something like that, okay, right? When we were discussing molecules detected in space, what was the largest molecule we kind of saw in space? In terms of molecular formula, in terms of the molecular architecture, what is it? We saw something like molecules such as C60, right? Being detected in space, right? C60, one of the largest. Perhaps, I'm not sure, but if I dig deep into the literature, some C60 times n, may also have been detected in space, but the detection of C60 is actually definitive. So we'll consider it as one of the largest molecules detected in space. And this molecule, C60, right? It is like very well known. I think probably since 2018 or something, right? It is very well known that even this molecule, okay, right? This molecule behaves as a wave particle. How does it behave as a wave particle? Well, it exhibits interference patterns. In other words, exhibits interference. This is interference pattern, right? Which means its wave-like nature is well known. And of course, right, this is one. So as a wave, it exhibits interference patterns. But what about as a particle? How does anything exhibit a particle type nature? Well, to begin with, it has a well-defined mass, right? It has a well-defined mass. Well-defined molecular mass, molecular mass, etc., etc., right? Which means that it is going to be a particle. So I'm writing, way below, so the handwriting may not be really that well. I'll read this again for your benefit. This says well-defined molecular mass, etc. So this behaves as a particle. So as a wave, right, it exhibits the interference pattern, and of course it's a particle because it has its mass well-defined. So all the particle type nature is also going to be exhibited. So therefore, right, when one of the largest molecules, right, one of the largest molecules in space, when that exhibits wave-particle duality, then of course molecules which are much smaller than this, we call your lambda is lambda de Broglie. The de Broglie wavelength is nothing but h over p, right? So when the largest molecule exhibits wave-particle duality, molecules which are lighter than this, that is like molecules whose molecular mass is less than C60, right? Even they are going to be exhibiting wave-particle nature. So more or less, it can be said with certainty that the wave-particle duality is prevalent in almost all of astrochemistry. And that is why, that is why I took the effort to make you go through the de Broglie wavelength as part of astrochemistry when you keep studying that content in your 11th and 12th standard itself, right? And you studied in so many other contexts, modern physics, atomic chemistry, quantum chemistry, etc., etc. All right? So this is the relevance for this de Broglie wavelength and the Schrodinger wave equation subsequently in the context of astrochemistry. This was page 2. So in fact, I'll just give you a snippet, okay, a snippet associated with this idea. Snippet. It is that, see, on Earth, okay, forget space. On Earth, it's an interesting idea. On Earth, so this idea that C60 exhibits wave-particle duality, I think I earlier said it as 2018, but no, it's actually been known since roughly 99 or 2000. Okay, when it was a Nature publication where it was seen that C60 also exhibited interference patterns. It basically exhibited an electron diffraction pattern. Okay, right? So this is C60, but on Earth, okay, beyond C60, what is the molecular mass of C60? If you assume that, like carbon-12 is the dominant isotope, then C60 is 60 times 12. What is 6 times 12? 60 times 12. 60 times 10 is 600. And 60 times 2 is 120. So 60 times 12 is going to be 720, right? So molecular mass of 720 grams per mole, right? That exhibited wave-particle duality. But on Earth, if I'm correct, okay, a polypeptide, that is, when I say polypeptide, I'm talking about a molecule containing this linkage. N times. This is the fundamental unit present in a lot of proteins. Okay, so this linkage weighing approximately close to 1882 grams per mole. The molecule's name, if I recollect correct, is either gramicidin or garmicidin. And it is roughly a system containing C99 something, it's a C99 system containing some nitrogens, oxygen, etc., etc. Okay, right? So this polypeptide, so it's not just a molecular mass of 720, but even a molecular mass as large as 1882 that exhibits wave particle duality. And this is just a snippet to tell you, that even polypeptides, which are very large molecules, right? Even they exhibit wave particle duality. And as a corollary, there's actually no well-defined boundary as to where exactly does something small stops behaving like a wave particle and starts exhibiting purely particle type nature. There is no well-defined boundary, but please understand that In space, it is definitely relevant. And on Earth, for a lot of molecules, including large molecules, it is relevant. So that is the idea behind this question. Okay, we'll now move to our next question, which is also on the topic of de Broglie wavelength. This is going to be, one of our classic true or false type questions. The statement given to you is, so you should say whether it's true or false, the statement, and also explain why. So the true or false. The statement is that the de Broglie wavelength, I'm just going to call this like lambda dB or lambda d, okay, for de Broglie wavelength of any substance is the same as lambda, that is like the traditional wavelength, okay, right? Lambda that one studies, that one encounters, okay, that one sees in waves, right? Recall that we were studying about the different properties of waves and particles, right? And I introduced you to the notion of wave particle, which could be quantified via the de Broglie wavelength. Now, is this de Broglie wavelength the same as the wavelength that we study when we study waves? After all, waves, wave particles, well, is it same or is it different? This is a fundamental question related to physics. So answering this would help us gain a better understanding of what are waves, what are particles, etc. So what do you think is the answer? The answer is this statement. This statement is it true or is it false? This statement is false. Okay. Please note that the de Broglie wavelength is specifically, it was specifically designed for the purpose of quantifying the wave particle character, that is lambda d, which is given by h over p, right, is designed to quantify the extent of wave particle duality. Whereas, right, your wavelength of a wave, right, your wavelength, right, which is defined by the c equals mu lambda, yeah. So which is defined by dividing the frequency, dividing the wave velocity by its frequency, or if you want to use the more conventional notation, c by mu, right? So this is going to be meters. This is going to be meters per second, and this is going to be per second, right? So you get meters here. Likewise, this is meter, but the units come about in a different way. This is going to be joule seconds, and this is going to be what? This is mass time velocity, and when you cancel the units, it's going to be meter in a different way. Okay, right? So we've of course derived the units in the lecture itself, so I'm not going to repeat it once again. Okay, right? So this is meter in a different way. All right. So this is not the same as this. So your lambda d is not the same as lambda, as you can see from the math itself, right? So the wavelength is a fundamental property of a wave. Okay, this is a fundamental property of a wave, whereas the de Broglie wavelength can be defined for anything. The de Broglie wavelength can be defined for anything, but a wavelength can be defined only for a wave. Okay, so please note this difference. The de Broglie wavelength is not the same as the conventional wavelength that you encounter in the study of waves. Okay, so this was just a fundamental question to make sure that your basics are 100% clear. Okay, we move on to the next question now. So that was the second question, in fact. So we move on to the third question now. I mean, this is also kind of true or false type questions. Now, in the lectures, we were discussing that spectral signals are discrete, right? Spectral signals are discrete, and the discretization is as a result of quantization, and the quantization was as a result of imposing boundary conditions, right? Or in other words, imposing restrictions. Okay. Now this question is concerning that. The question is that in spectra, recall, what do I mean by spectra hereafter? I said in the previous lecture, right? A few lectures ago, I was saying that the spectra is no longer, merely a list of energies, right? but it is going to be a plot of intensity of the line obtained from the intensity of the line obtained, right, due to the incoming radiation, right, versus some frequency wavelength or something like that. Okay, right? So when I say spectra hereafter, please recall it's no longer a list of energies, but a plot of I versus nu, lambda, wave number, etc. Okay. All right. So in spectra, the lines we obtain, or I'll put it this way, instead of lines, right, I'll call it the signals we obtain. I'll also say by spectra, I means it's a plot of I versus nu. I'm just writing nu for the sake of brevity. It could be lambda, it could be wave number, anything. Okay. So in spectra, the signals we obtain, right, not obtained, obtain, are always discrete. This is yet another important point, which we often tend to ignore. Okay, what did we see in the class? We saw that the lines, the atomic spectra obtained from sun, they were all discrete. We also saw that it is from the discrete lines of electronic transitions corresponding to CH plus, CH, and CN that we could detect these molecules in space. Similarly, the ammonia inversion was also a discrete line. Okay, right? So is it true that the spectra we obtain always correspond to discrete lines? What is the answer? Well, intuitively, and we have a tremendous inclination to say yes, right? It's always discrete. Otherwise, why would we ask it? The answer, as it turns out, is no. Because discrete spectra, okay, right? Note this point. Discrete spectra are obtained only when we deal with bound systems. Recall. I've always been telling, right, that discretization in the spectra, in the spectral signals obtained is possible only when we deal with bound systems. For example, this is page number 3, and this is page number 4 now. I will illustrate it with the example of the potential energy surface, the representation of a potential energy surface we discussed a few lectures earlier. And why should discrete spectra be obtained for only bound systems? Because it's only with bound systems that we have a boundary condition. So with bound systems, I'll write it here, we have a boundary condition, right? And this boundary condition results in quantization, and this quantization is what results in discrete spectra. Are we good, right? So the key is, we should not just be discussing about any quantum mechanical entity, but it's a quantum mechanical entity that should be a bound state. Okay, let's try to understand it from the miniature version of a potential energy surface we discussed in class. For example, what did we see? We saw that this is the potential energy curve as it varies with R, right, for a diatomic molecule, for a sample diatomic molecule. Now, where is let's of course ignore this region, okay, right? This region where I'm just going to call this A, which is the equilibrium bond state, right? The equilibrium state. And let me call this region B, and let's call this region C, right? To the right of A is C, to the left of A is B. We ignore region B because there the nuclear repulsion is going to be predominant. So chemically, we're not interested in that region, okay? Now, if you consider regions A, right? In region A, the molecule is close to its equilibrium bond length, okay, right? In other words, in A, the molecule is close to its equilibrium bond length, right? Now, what happens as a result of this? What happens as a result of this phenomenon is that, the electrons and nucleus are tightly bound. And when you measure the spectrum in this region, very close to this region, right? So when you measure the spectrum in this region, I'll call it region A. Okay, right? So spectrum measured in region A, right? So the spectrum, I'm just going to call it SP, okay, spectrum will lead to discrete lines. Please note this carefully, okay, right? So the spectrum when measured here will lead to discrete lines. But notice that sometimes it could be possible, okay, in fact it is routinely possible more and more these days to measure the spectrum in this region, that is in region B, so in region C, okay, right? So when you measure the spectrum in region C, right, where we're talking about a dissociated state. Right? Where when we're talking about a dissociated state, therein, okay, the electron and nucleus are no longer, bound to each other. The two nuclei are far away, right? And that's why, as we discussed in the class, we see that the energy doesn't change much because they are independent of each other, right? The two entities are independent of each other, okay? So the dissociated state, we do not have a bound system. There is no binding or bonding, right? Okay, there is no bonding, which means herein there is no quantization of energy. Please note this, okay, right? Which means no there is no quantization, and when there is no quantization, you shall not be getting a discrete lines, and this means in region C you shall be getting a continuous spectrum. Okay, please note this point very clearly. All right, it's exceptionally important, in fact. Okay, so it is not always true that we shall be getting a discrete spectrum, but the information from a continuous spectrum, right, is not going to be as important to us in astrochemistry because it's only through discrete lines that we can separate out, right? Separate out the energy levels, and we can see that, oh, this molecule or atom, right, when it undergoes excitation and comes back to its ground state, is going to give rise to this signal at this specific wavelength. All right, that is the use of discretization. Okay, so discretization therefore has this use, and it is valid only for bound states. Are we all good? So please note this point also. This is going to be a recurring theme many times in spectroscopy when we obtain the spectra of species which are not bound. Okay, and this is from our perspective in our class, right? We are much more concerned with this region, a region close to the equilibrium bond length, wherein we understand that the state we are describing is a bound state, and so therefore the spectral lines are going to be discrete, and from that we can get the molecular signatures corresponding to various transitions through which we can deduce the structure of a molecule. Okay, so that is the logic behind this question, where we were discussing about the discreteness and the continuous character of any spectrum obtained. Okay, all right, we'll now move on to the next question. I'll delete this part now. So while on the topic of discretization and quantization, right, I want to clarify some aspect from a lecture. Okay, right? I'll just call, this is not a question, but this is just a clarification from lecture. Right? In the lecture, right? Say you can go back to say, lecture 36 or 35, around therein. Okay, you can see that we were discussing about the energy of the quantum mechanical entity whose motion was restricted, right? That was going to be given by n square h square by 8 ml. Yeah. So yeah, the pi would get cancelled out. Yeah. Okay. So this is the eventual expression, right? N square h square by 8 ml, where n equal to 1, 2, 3, etc., etc. Okay. Now this problem, okay, right? This problem is mostly not directly relevant to any physical situation. Okay, I want you to clearly understand that. Okay, right? This expression, okay, right, is mostly, you can come up with some applications concerning very large hydrocarbons which are conjugated and all that. Okay, don't worry if you didn't understand my last sentence. Okay, but more importantly, this expression is mostly not relevant in practical spectroscopy. Okay, especially as we concern ourselves with the detection of molecules in space. Nonetheless, we studied this. Okay, we studied this, right? We studied this particular model that was restricting the quantum mechanical entity's motion because it teaches us about quantization. About quantization. And that quantization arises due to boundary conditions. Right? So, in fact, I will slightly be modifying this statement. This expression is mostly quantitatively not relevant. Okay, I'll put it this way. Not quantitatively. Quantitatively. Okay, that means, the energies obtained, right? If you want to calculate the energies between any two levels from this expression, they might mostly not match from the actual spectra obtained. But nonetheless, as a qualitative model, this teaches us why quantization arises. Okay, right? And that is why we studied this, to understand discretization and how via discretization we can get the spectral. We can understand the molecular structure, right? And that's how we get to know that there are molecules in space which are also found on Earth. All right. So that is why we studied it. Okay. So the clarification is this particular expression is not going to be as such relevant. This is what is called as a toy problem, in the lingo of physics. Okay, right? This is a toy problem that we study to understand much more conceptually important aspects. Okay, much more conceptually important aspects in astrochemistry, such as, for example, when does quantization happen and when are the lines discrete, etc., etc. So please never be confused that this is the expression. This is the exact expression used. For example, in analyzing any spectrum. Okay, it is not. We are just studying it to tell you clearly that, hey, this expression teaches us about quantization of energy, and the same idea is applicable to other problems as well. Okay. On that note, I end this tutorial, and we shall continue with more problems in the next tutorial. Thank you so much.